Advanced Dimensionality Reduction Techniques Part 1. By the end of this topic, you will be able to describe and explain why adjusted R-square metric is better for dimensionality reduction. In the last module, we learnt about the simpler dimensionality reduction techniques and how to implement them. But we got an idea that simpler dimensionality reduction techniques have very subjective criteria for dimensionality reduction, which can be a source of confusion if these criteria are not clear. Worse, it can lead to poor model performance due to accidentally eliminating some important features. In this video, we will be looking at some of the advanced and mature dimensionality reduction techniques, namely forward selection of features and backward elimination of features. To undertake the process of feature selection using the forward selection and backward elimination, we will need an evaluation metric which will govern whether any given feature should be deselected in the final model or not. So before we dive into advanced feature selection techniques, let's take a closer look at the adjusted R-squared metric which we covered in the previous module briefly. Previously, we covered that R-squared does not consider the number of input variables in the model, and therefore the R-squared values keeps on marginally increasing even if the newly added feature has zero to minimal importance. To counter this issue, we briefly discussed adjusted R-squared value. The primary characteristics of adjusted R-squared is that it considers the number of input features being fed to the predictive model. As a result, adjusting extra features with no significant effect on the dependent variable can reduce the model performance, that is, adjusted R-squared. Now let's see how this happens. The formula of the adjusted R-squared is shown on the screen, where n represents the sample size or total number of observations. K represents the number of input variables in our regression model. R represents the simple R-score. In case of mean regression model, there was no input variable considered, and hence the value of k equal to 0, which makes adjusted R same as R. To understand it better, let's extract the needed relation from this formula. Now let us consider the two cases. New feature added contributes significantly to model performance. New feature added does not contribute significantly to model performance. In case 1, when we add the new feature to the model which contributes significantly, the increase in the value of simple R is substantial and can easily overwhelm the incremental increase in the value being decreased by adding a new input column. As a result, there is an overall increase in the adjusted R value. In case 2, when we add a new feature which is not contributing significantly to the model performance, there is little or no increase in the value of normal R, but there is some incremental increase in the value of k. As a result, adjusted R experiences a slight decrease in its overall value. Hence, if you are building a model on multiple variables, it is always suggested that you use adjusted R to judge the goodness of the model. Typically, the more non-significant variables you add into the model, the gap in R-squared and adjusted R-squared increases. Now that we have understood the adjusted R, we will now be looking at the implementation of the adjusted R metric. Note that scikit-learn does not have adjusted R variable in its library. As a result, we will be implementing our own version of adjusted R in Python. We define a function called adjusted R2 which will take 3 parameters. Data x, that is the data containing the independent variables. Data y, that is the data containing the labels. And predictions, which are nothing but the predictions generated by the regression model. Now inside the function, we will import the R2 score from the scikit-learn library, so that we will not have to calculate the R from scratch. Next step is calculating the simple R score for the predictions made. For this, we will simply use the R2 score functions with data y and predictions as the parameter. We will store the result in the R variable. Next step is to extract the number of independent variables and the number of observations on the data. For this, we will be using len data x columns and len data y and store the results in m and n respectively. Now that we have all the variables ready for the calculation of the adjusted R, we will code the formula and store the results in variable adjusted R. Lastly, we return this result. Let's test this on the linear regression model that we built previously. So in this notebook, we have taken care of every step except the last one, which we described a while ago. We can clearly see that using all the variables of the transformed housing data 2.csv, we get the R score of 0.8462. Using the previously defined function, we passed the m data and the predictions to this function as the parameter. Note that m represents the number of independent variables. On running this cell, we get the adjusted R score as 0.845. On comparing, 0.8452 is marginally smaller than the simple R score. This result guarantees that there are some features which are not adding value to the final model. Now that we have understood the adjusted R squared, we will now shift our focus back to the forward feature selection and backward feature elimination techniques, which use the concept of adjusted R squared to eliminate such insignificant features. We will begin with forward feature selection technique in the next video.